What up, everybody? InstructaBeats back again here with our probability unit. Today we're going to be using a tree diagram to make a non-uniform probability model. So let's take a chance and see what our objective is today. But first, let's start with some mathvocabulary. So a compound event, we talked about that last lesson, is when two or more events are happening at the same time. In last lesson, we did everything was a uniform probability model, right? All the different outcomes had the same probability of happening. Today, we're focused on non-uniform probability models. So a non-uniform probability model is when the outcomes have different probabilities. So it might be a 2/3 chance that you land on 6, and a 1/5 chance that you land on 2. Okay, whereas last lesson, everything was uniform. Everything had the same probability. Let's take a look at this conceptually. So last lesson, we talked about doing tree diagrams and organized lists and tables to help us find the probability of independent compound events, right? And so if we had two coins being flipped, we could either have heads or tails. And then if you flipped it again, you could have heads or tails. And then if you flipped it again, you could have heads or tails, right? So the different outcomes would be heads, 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 tails, tails, heads, or tails, tails. And if you notice, this is what we call a uniform probability model because all of them have the same probability. It's all 1/4 or 25%. You can expect all of these outcomes to happen 25% of the time. And in a probability model, it's important that all the probabilities equal one whole, right? So when you add up 1/4 plus 1/4 plus 1/4, that's going to give you one whole because remember on our probability line, 1 means you're certain. So if you're at a 1, that means we are 100% certain that one of these is going to happen. And so this is what it looks like for a uniform probability model. Let's take a look at a non-uniform probability model. So our we do problem says Leah has a bag of marbles. Okay, there are 3 green marbles, 2 blue marbles, and 1 red marble. She pulls one randomly, writes the color down, and then puts the marble back in the bag. That's supposed to say bag. There we go, not back in the back. That wouldn't make any sense. Then she does it again. Okay, so this is important because since she's putting the marble back in the bag, this makes it independent. All the times that she draws a marble out don't affect the other times. We want to make a probability model to help us answer these questions. So the first thing we're going to do is we are going to do a tree diagram. Okay, so on our first draw, she can either draw green, she can draw blue, or she can draw red, right? These are the 3 different options or outcomes that are possible. So then we make our tree map here, draw our limbs out, and then after she does that, she's putting it back in the bag, right? Which means she can draw another green, blue, this should be a B for blue, or red. Okay, and we draw our limbs there. You can draw arrows if you want. If she draws blue, guess what? She still has all 3 options because she's putting them back in the bag. And the same thing if she pulls red. Now it told us that she did this twice, okay, because it said she did it. That was event 1, and then she does it again. So our outcomes that we could have, we got to continue our probability model, would be GG, good game, green blue, or green red. Or you could do blue green, blue blue, or blue red. And then you could have red green, right? Red blue, or red red. These are the different options or the outcomes for this experiment. Except, of course, we forgot one thing, right? The green, the blue, and the red are not equal. They're not in equal amounts. It's not like the 6-sided die where there was one side each had a number on it, okay? These are non-uniform, okay? So which means we're going to do the same tree model, but now we need to make sure we write down the probability. So for our first event, we know that we have 3 green, 2 blue, and 1 red, right? That's going to give us a total of 6. So the probability of pulling a green one out, because there's 3, that means there's 3 different ways it could happen, would be 3/6, or you could simplify that to 1/2, okay? Matter of fact, I'm going to leave it as 1/2. For blue, again, there is still 6, right? But there were 2 different ways to do that. So you could do 2/6, and then that could simplify down to 1/3. It's important to simplify the fractions because it's going to help you when you do the next step. For red, it was only 1 out of 6. So you can see this is not uniform probability because there's more green. That means there's a better chance. There's a 50-50 chance that you pull a green one. Because there is 2 blue, right, you're at about 33% of a chance. So you're unlikely to pull blue, and if you're red, you're even more unlikely because you're closer to 0, right? This goes back to our probability line that we talk about. So now, because you put the marble back in, the odds are the exact same again. So for you to pull green again would be 1/2, okay? For you to pull blue would be 1/3. For you to pull red would be 1/6. So the way this works is, this is called the multiplication rule for independent events. All you're going to do is you're going to multiply your probabilities like you're multiplying fractions, and that will tell you the probability for your outcomes. So if you pulled green first, that's 1/2, right? So then 1/2 times, if you pulled green again, that was another probability of 1/2. So 1/2 times 1/2 means you have a 1/4 chance of pulling 2 greens. If you kept going, 1/2 to pull green, and then it was 1/3 to pull blue. So if you do 1/2 times 1/3, you have a 1/6 probability of pulling a green and a blue. Green red would be 1/2 times 1/6. So you have a 1/12 probability of pulling a green first and then a red. So you're just using your fraction multiplication following the multiplication rule of independent events. So if you kept going, okay, you have 1/3, and then you had a 1/2 chance of pulling out green. So 1/3 times 1/2 would be 1/6. So you have a 1/6 chance of pulling blue and then green. Blue would be 1/3 times 1/3, which would give you a 1/6 chance of pulling out 2 blue. Sorry, 1/9. Gotta do my math right. You have a 1/9 chance of pulling out 2 blues. If you pulled out a red, that would have been 1/3, and then it was a 1/6 probability you pull out a red. So then you would have a 1/18 probability of pulling out red. So you're just kind of following your limbs and multiplying the fractions. That's kind of the shortcut. So same thing here. 1/6 times 1/2 gives you a 1/12 chance of pulling out a red and then a green. 1/6 and then 1/3 gives you a 1/18 chance of pulling out a red then a blue. And then the least likely would be to pull out a red, and that would be 1/6 times 1/6, which is 1/36. So you're doing the exact same thing, except now you have to think about the probability because it's not a uniform model. There's a different probability for pulling out each marble because they weren't equal. So you write your tree map out, you write down your probabilities, and then you just follow your multiplication. Let's do a U-try problem. So it says Miguel and Lily are shooting free throws. Miguel made 3 out of 10, and Lily made 8 out of 10. They both shoot one more free throw. What is the probability that they both make it? So pause the video, try to make your tree diagram. If you need help, you can just wait. We can do it as a we do problem. But if you can, try it out and then push play to check your work. So hopefully you just paused it and now you're checking your work. So it doesn't really matter who goes first. I'll just put Miguel first because he was here. So Miguel's going to shoot free throws, okay? And he's either going to make or he is going to miss, right? And so I'm going to put this right here. And Miguel has a experimental probability of 3/10, right? He made, so the experimental probability of him making it is 3 out of 10, okay? Which means he missed 7 out of 10, okay? So we can see that we're going to do this question with experimental probability, not theoretical probability. And then Lily shot hers, and if Miguel makes it, right, there's still 2 options for Lily. She can either make it or she can miss it. There, oop, my arrow's uneven, but that's okay. And Lily has a experimental probability to make it of 8/10, which I'm going to simplify to 4/5. Okay, so we're going to have 4/5 for making it, which means 1/5 that she missed it. Missing it would be the complement to making it, which means we go back to what we talked about with complements of an event. They have to equal 1. If she shoots the ball, she is 100% sure that she's either going to make it or miss it. Something is going to happen, which means our events have to equal up to 1 to make it certain that something is going to happen. If Miguel misses it, I'll come over here, okay? Lily still has the same 2 choices. She can either, well, not really a choice, but same 2 options. She can make it or miss it. And her experimental probability is still 4/5 to make it 1/5 to miss it. So we want to know what's the probability that they both make it. So if it's 3/10 that Miguel makes it and 4/5 that Lily makes it, we know that 3/10 times 4/5 equals 12/50, which we can simplify to 6/25. So we're going to say the probability of having 2 makes on our next shot is 6/25. If they both shot one more, okay, and they did that 25 times, we'd expect both of them to make it only 6 out of those times. Thank you so much for checking us out today. We really appreciate it. We hope you'll check out our probability song and the rest of our probability unit. We would love for you to like the video and subscribe, comment, let us know where you're watching from. We appreciate you. Thank you. InstructaBeats out.